Welcome to The Explainer. Today, we are looking at a cosmic mystery that is so massive, it basically backs us into a corner. You see, it tells us one of two things must be true. Either 85% of all the matter in the entire universe is completely invisible to us, or our most fundamental understanding of gravity, the one built by Newton and Einstein, is just plain wrong.
Okay, so let's dive right in. The problem really starts here. When we look out at those beautiful spiral galaxies, we see that the stars way out on the edges are moving way too fast. I mean, they're moving so quickly they should just be flung off into deep space, kind of like kids flying off a merry-go-round that's spinning out of control. But they're not. They're sticking around. So the big question is, what's holding them in?
Well, for decades now, the standard explanation has been this. There's a huge invisible halo of something surrounding every galaxy. We call it dark matter. We can't see it, we can't touch it, we can't detect it in any way except for its gravity. The idea is that its immense gravitational pull is what's keeping all those speedy stars in line. And you know what? It's a pretty clean and effective fix to the problem.
But what if we've been looking in completely the wrong place for an answer? A physicist named Erik Verlinde suggests that maybe, just maybe, instead of inventing a whole new kind of stuff to make our theory work, we need to take a hard look at the theory itself. What if the problem isn't that there's matter we're missing, but that there's a deep misunderstanding of gravity? So this is really the crucial point. This one single observation about how galaxies spin forces us down two totally different paths. We either have to add a whole bunch of new ingredients to the cosmic cookbook, or we have to change the recipe itself.
For a long time, the add more stuff camp has really been the dominant one in physics. I mean, we've built these enormous detectors buried deep underground, all of them hunting for these phantom dark matter particles. But the change the rules camp, they're asking a much bolder question. What if we're not missing a particle at all? What if we're missing a fundamental piece of the puzzle about how gravity actually works?
And what's so fascinating is that Verlinde's idea didn't come from studying galaxies. No, it came from studying the most extreme, the most bizarre gravitational objects in the entire universe, black holes. It turns out the clues to a whole new theory of gravity were hiding where gravity is at its absolute strongest.
Okay, so this whole story really gets going back in the 1970s, and it starts with a thought experiment. Physicists Jacob Bekenstein and Stephen Hawking were thinking about black holes, and they realized something that seemed, well, impossible. These cosmic destroyers, they weren't just simple bottomless pits. They discovered that black holes act as if they have a temperature and something called entropy, which is really just a fancy way of saying a measure of hidden information. Now, this was absolutely revolutionary because it connected gravity to the laws of heat and information in a way nobody had ever even dreamed of.
And this is where it gets really weird. For just about everything else in the universe, a box of gas, a planet, a star, the amount of information it can hold depends on its volume. Makes sense, right? The more space you have, the more stuff you can pack in. But what they found was that a black hole's information is proportional to its two-dimensional surface area. Think about that. It's like all the data for a huge 3D movie being stored only on the thin surface of the screen itself. This completely broke the rules and was a huge clue that something much deeper was going on with gravity. This totally bizarre area law was a profound hint. It suggested that maybe gravity itself, and maybe even our entire three-dimensional reality, might be a kind of projection. And that leads to this truly mind-bending concept called the holographic principle. Just try to imagine for a second that our 3D universe is actually like a hologram being projected from a distant, flat 2D film. The idea here is that everything happening in our 3D world, you, me, the stars, everything, is just a projection of information that's encoded on that far-off 2D surface. And here's the kicker. What we experience as the force of gravity might just be a shadow of simpler physics happening on that 2D film.
So if you follow this train of thought, physicists realize something absolutely stunning. If you start with these basic rules about how information behaves, the laws of thermodynamics that govern heat and disorder, you don't even need to assume Einstein's theory of gravity. His famous equations just sort of emerge from the math. It just pops out. This suggests that gravity might not be a fundamental force of nature at all. Instead, it might be what we call an emergent phenomenon, kind of like how temperature isn't a fundamental thing, but emerges from the collective motion of countless tiny atoms.
Now this is where Erik Verlinde really comes into the picture. He took this incredible abstract idea and he asked a really critical question.
Okay, that's great, but what happens when you apply this concept not to some perfect theoretical model, but to our universe, the real one?
You see, all of this foundational work, this holographic stuff, it was all worked out in a very specific theoretical kind of space-time. It was a nice, tidy theoretical sandbox, and, crucially, it was a universe that didn't have any dark energy in it.
But that's not our universe, is it? Our universe is messy. It's filled with this mysterious force we call dark energy, and it's pushing space itself apart faster and faster every second. And believe me, this isn't some minor detail you can just ignore. It fundamentally changes the geometry and the entire information content of spacetime.
And this is Verlinde's key insight. He argued that dark energy isn't just pushing space apart, it's also filling the universe with a completely new kind of information. Remember how the information in a black hole lives on its surface? Verlinde proposed that the information from dark energy lives everywhere, woven into the very fabric of space itself. It's this deep underlying layer of complexity that's spread throughout the entire volume of the cosmos.
And here is the absolutely brilliant twist. This extra information, this quantum data woven into the vacuum of space, it isn't just sitting there passively. Verlinde argues that it actively responds to the regular matter within it, and in doing so, it creates this subtle, extra, long-range gravitational pull, a kind of ghost gravity that you just won't find in Einstein's original equations.
So now we can finally circle all the way back to those galaxies that are spinning too fast. But this time, we're armed with a completely new tool to try and solve the mystery.
You see, this emergent gravitational pull that comes from dark energy's information is incredibly weak. In our solar system, for instance, you'd never even notice it. But it becomes significant over the vast distances of an entire galaxy, which is exactly where we see those stars moving too fast. It provides just enough of an extra tug to hold the galaxies together with absolutely no need for dark matter at all.
This whole situation frames the debate perfectly, using a bit of history. Back in the 19th century, astronomers saw that Uranus was wobbling in its orbit. They predicted it was because of another planet, and they were right. They found Neptune. That was a classic case of adding more stuff. But then they saw Mercury's orbit was also a bit off, so they proposed another new planet, which they called Vulcan. But here's the thing. Vulcan didn't exist. The real answer was that they needed a whole new theory of gravity, which turned out to be Einstein's general relativity. So the big question for us today is dark matter our Neptune, or is it our Vulcan?
So, the key takeaway here is that while Verlinde's theory is definitely still a work in progress, it's still being tested and developed, it represents a massive shift in how we think about the universe. It challenges us to consider that the answers to our biggest cosmic puzzles might not be found by just searching for new things, but by reaching for a fundamentally new understanding of reality itself.
And all this leaves us with one last fascinating question to chew on. Are we living in a universe that's fundamentally made of physical stuff, particles and forces? Or is reality something far stranger, far more abstract, a universe built not from matter, but from bits of information and quantum entanglement, where even space and time and gravity are just part of a grand emergent illusion?